In this video, we'll do a review of quantitative chemistry and we'll look at some common examples that come up. So the first question is empirical formula. So with an empirical formula question, you should start by writing the elements involved at the top and then underneath write the percentages. So that's 12, 72, 12 and 16. And then you divide by the molar mass. So for carbon it's 12, hydrogen it's 1, and oxygen is 16. Now notice I'm using numbers to two significant figures because this will be a multiple choice question and you should be given relatively easy numbers to work with because you're not allowed to use a calculator on paper 1. Okay, so once you divide there you should get 6, 12 and 1. So then we write the elements in order, the atoms in order. C6H12O, and it's asking for the C to H ratio in the empirical formula. So we got 6 to 12 and that can be simplified down to 1 to 2. So the correct answer there is B. So moving on to question 2. This is a moles question. You're given mass and you'll have to calculate the molar mass of sodium hydroxide. So we'll use the equation number of moles equals mass over molar mass. Okay, so that's 2.0. And I'm going to use the molar mass just to be 40. Again, I'm using easy numbers because these are multiple choice questions. And you should get 0.050 moles of NaOH. And you will have to be fairly confident at doing these kind of calculations without a calculator. Okay. So the correct answer there is A. So moving on to question 3. This is a gas question. So for a gas to have the greatest volume, which two conditions? And here's your choices. So the greatest volume will be high temperature and low pressure. So an ideal gas will have the greatest volume under these conditions. So you can see that D is the right answer here. Moving on. This is a stoichiometry question. So you have 58 grams of butane, which is C4H10. So the first thing you have to do is change that to moles. So I'm going to use, again, N equals molar mass, mass divided by molar mass. So the mass is 58 and the molar mass of butane is also 58. Again, we're using simple numbers, two significant figures, and that gives us 1 mole of C4H10. So the question is asking how many moles of CO2. So next what we do, we look at the ratio of, the ratio of butane to carbon dioxide, because the question is asking about carbon dioxide. So ratio of C4H10 to CO2. So you look at the coefficient, the number in front, and it's a 2 to 8, and that can be simplified down as a 1 to 4. So if you have 1 mole of butane, you're going to make 4 times as many moles of carbon dioxide because it's a 1 to 4 ratio. So the answer here is A4. Okay, right, moving on. I'm going to skip these. My advice on balancing equations is to leave them to the end because they can take a lot of time to do, and bear in mind you're given 2 minutes per multiple choice question. So if you're spending more than 2 minutes on this question, you're wasting your time. It's only worth 1 mark anyway. So I'm just going to skip those. I might come back to them at the end. Okay, so next we have another empirical formula. This one is slightly longer, but the method is the same. You write down the elements involved, so that's C, H, and N. You will have to do a little bit of calculating to find H because you're not given H, okay? So that's 24.1, and the remainder there, if you subtract all these from 100, will be 13.9, okay? So then you divide by the molar mass, and I think that's 14 if I can remember correctly, and that's 1.01, and we get, I think if I've done my math correctly, you get 5.16, 1.72, and 13.9 or thereabouts, okay? And then you divide these by the smallest, so divide them all by 1.72, this one too, and then you should get numbers that are close to 3, 1, and 8. And then you write down the formula at the end, C3NH8. Students often ask, does it matter the order that you put these in? Not really. Carbon should come first, but you could have C3H8N. That'd be fine too. And then you have to define the term relative molecular mass. It's the mass of a molecule relative to carbon 12. Or you could have the extended version, which is the weighted average mass of a molecule relative to 1 gram of carbon 12. Okay, part 3. The relative molecular mass of A is 116. Determine the molecular formula of A. So basically, we know that the empirical formula is C3NH8, and if you add those up, you get the so now we're on to part 3. The relative molecular mass of A from part 1 is 116. Determine the molecular formula of A. Okay, so the empirical formula is C3NH8. And if you add up the mass of all these atoms, you should get 58 or thereabouts. Okay, and then the relative molecular mass is 116. Divide that by the mass of the empirical formula, which is 58. And you should get 2. And then you multiply the whole empirical formula by 2, gives you C6N2H16. And that's the molecular formula of A. Okay, on to question 7. Now this is a question that students often get wrong. And what they do, they see the question, they see the words, how many hydrogen atoms are contained in ethanol? And they think, okay, so that's 5 there and 1 there, and they choose B, and they get it wrong. The reason they get it wrong is because they're not taking into account this part, 1 mole of ethanol. So if we had 1 molecule of ethanol, I'll quickly draw the structural formula for ethanol here. This is 1 mole of ethanol, sorry, 1 molecule of ethanol here, so 1 molecule. And 1 molecule has 1, 2, 3, 4, 5, 6 hydrogen atoms. But we're forgetting the question's asking about 1 mole. So 1 mole equals Avogadro's number of anything. So that's 6.02 times 10 to the 23. So you have to multiply the number of hydrogen atoms in a molecule times Avogadro's number. So what you have to do is actually this calculation here. And remember, this will be without a calculator because it's from paper 1, but the math is fairly simple and you should be able to work out it's D. So be careful for this kind of question. Okay, number 8. Again, it's a moles question, and you have to use Avogadro's number. So you're given the what amount of oxygen contains that many molecules. Okay, so what you have to think is this: 1 mole of O2 equals this many Avogadro's number of molecules. But we don't have this many, we only have this many, 1.8 times 10 to the 22. So we divide that by Avogadro's number, and we get approximately 0.030. It's actually 0.299 something, but we can round up to that, so the correct answer there is B. Right, we're on to a gas question next. How would you increase the volume of a fixed mass of gas? So you have two conditions. You have pressure and temperature. So basically, if you double the temperature, you double the volume. And if you double the pressure, you halve the volume. Boyle's law and Charles's law. Okay, so if you change these conditions like it is in A, you double the pressure, well, the volume would halve, and then you double the temperature, the volume would double. You'd be back to where you started. Okay, and you can try for B, C, and when you get to D, if you halve the pressure, you double the volume, and then you double the temperature, you double the volume again. That would increase the volume. A, B, and C would either make no change or actually decrease the volume. So the correct answer there is D. Right, number 10 is one that catches a lot of students out because they don't read the question properly. It says empirical formula. These are not empirical formula. Empirical formula is the lowest whole number ratio of atoms, isn't it? So we can divide this by 2 to give you CH3. That's the empirical formula. We can also divide this to C2H5. This could be CH2, and this is CH. So now we can see that the empirical formula with the greatest mass is this one. So the correct answer is B. So be careful with this kind of question. And we're on to a gas question. So 3 decimeters of sulfur dioxide. We have 3 decimeters of this. And we have 2 decimeters of oxygen. And how much of this do we make? Well, you have to kind of figure out which one is the limiting reactant here. And you can do it fairly simply. The ratio of oxygen to sulfur dioxide is 2 to 1. So for us to react 3 moles of this, we need 1.5 moles of this. But we have 2 moles. On the other hand, to react 2 moles of this, we need 4 moles of this. We don't have 4 moles, we only have 3. So the SO2 is the limiting reactant in this case. So it's the SO2 that we use to determine how much SO3 we're going to make. Okay? And then you look at the ratio, which is 1 to 1, isn't it? It's 1 to 1. So if we have 3 moles of this, 3 decimeters of this, the answer is C. We're going to make 3 decimeters of SO3. So on to question 13. This is a percentage yield question, and you're given 50 grams of calcium carbonate, which is this here, and 7 grams of calcium oxide was formed. What's the percentage yield? So let's calculate how many moles of this we have, and then we can calculate the theoretical yield. Okay, so we're going to use this equation here. The mass is 50. And the molar mass of calcium carbonate is approximately 100. So that equals 0.50 moles of calcium carbonate. So you have to calculate the theoretical yield. How much would you make if the reaction went according to the stoichiometry? And it's a 1 to 1 ratio. So you'd make 0.5 moles of calcium oxide. Okay, and then you have to go to grams. So we use the equation mass equals number of moles times molar mass. So its number of moles is 0.50, and the molar mass of calcium oxide is 56. So that would give us 28 grams. So that's our theoretical yield there. So finally, we use the equation for percentage yield, which is actual yield divided by theoretical yield times 100. And I'm running out of space here. That is 7 divided by 28 times 100, And that gives you, after all that, you get 25%. So that's B. That's a lot of work just for 1 point, and you should be doing that in approximately 2 minutes as well. Okay, let's move on. We're on to a gas question. What will happen to the volume of a fixed mass of gas when its pressure and temperature are both doubled? So remember, pressure times 2 will be volume divided by 2. And temperature times 2, volume times 2. Okay, so if you double the pressure, you halve the volume, and then you double the temperature, you double the volume. So basically, it's A. It will not change. You're back to where you started, basically. Okay, let's move on to the next question. Okay, sodium reacts with water in this equation here to give you sodium hydroxide and hydrogen gas. And you have to calculate the concentration of the resulting sodium hydroxide solution. So whenever you're given grams, you must go to moles. So we're going to calculate moles first. So we're going to put 1.15 for the mass of sodium, and the molar mass of sodium is 22.99. Now notice that I'm using more precise values, which is 4 significant figures here, because this is from paper 2, and you'll be allowed to use a periodic table, so you should use those values on the periodic table. So that gives us 0.0500 moles of sodium. And then we have to calculate concentration, so we use the equation C equals N over V. And our N we've just calculated here, so that's 0.0500. And V, now you have to be careful because we're given centimeters cubed, but it has to be in decimeters because concentration is moles per decimeter. So we have to divide 250 by 1,000. And if you do the math, you end up with 0.200 moles per decimeter. So that's the concentration of our solution. Let me just tidy those up. By the way, that's a common mistake that students forget. They forget that V has to be in decimeters, so make sure you do that. Okay, and then moving on. What volume in decimeters of 0.3 mole per decimeter NaCl solution can be prepared from 0.60 moles of solute? So we're going to use C equals N over V. And if you rearrange that by multiplying both sides by V, so you get N equals CV, and then you want to find, what are we looking for here? Volume. So we want to divide both sides by C. We end up with V equals N over C. And we have our N, which is 0.060. And we have our C. Just check, yep, it's in moles per decimeter, so that's concentration there. And if we do the math on that one, we end up with 0.20 decimeters. Okay, so here's a limiting reactant question, and it's copper metal may be produced from the reaction of copper oxide and copper sulfide according to this equation here. So we have 10.0 kilograms of copper oxide and 5.00 grams of copper sulfide. Now what I would do is change from kilograms to grams. I think you can minimize your errors by doing that. So go from kilograms to grams, and you end up with Cu2O. We have 10.0 times 10 to the 3 grams. And then Cu2S, we have 5.00 times 10 to the 3 grams. So your next step is to change to moles. So I'm going to do that for copper sulfate, copper oxide. So we have 10.0 times 10 to the 3 grams. By the way, I'm using this equation here. And then the molar mass is approximately 143 to 3 significant figures, and that gives us 69.9 moles of copper oxide. I'll do the same for copper sulfide. 5.00 times 10 to the 3 grams divided by the molar mass of copper sulfide, which is 159. And if you do the math on that, you get 31.4 moles. So what you do next, you take those two numbers there, 69.9 and 31.4, and you divide by the coefficient in front. So for copper oxide, it's 2. Copper sulfide, it's 1. And if you do the math, you get 34.5 and 31.4. The lowest number is the limiting reactant. So the lowest number there is 31.4. So Cu2S is limiting reactant. Okay, so once again, you divide by the coefficient, and the lowest number you get is the limiting reactant. So in that case, it was Cu2S. So moving on to the next part, calculate the maximum mass of copper that could be obtained from these masses of reactants. So to calculate the maximum mass of copper, you use the limiting reactant. So how many moles of limiting reactant do we have? We have 31.4 moles. So it's 31.4 moles of Cu2S. What's the ratio of copper sulfide to copper? It's a 1:6 ratio. So that means if we have 31.4 moles of copper sulfide, we need to multiply that by 6 to get moles of copper. So that's 31.4 times 6, and that gives us approximately 188 moles of copper. But we're not finished yet because the question is asking for mass, not moles. So we use small m equals n times molar mass, number of moles times molar mass, which is 188 times the molar mass of copper, which is 63.55, and we get a number something like 11,972.82 grams. Now you have to be careful because we go back to the original question and the starting data is 3 significant figures. Okay, and here again. So we can't give that answer. That's far too many significant figures. So we can round up. And when you round up, you end up with something like 12.0 times 10 to the 3 grams of copper.